pretty cool piece of audio gear up on the workbench today to take a look at. It's a Lexicon PCM90. It's owned by a friend of mine, and he uses it in his studio and for sound engineering that he does. This was a working device, and it stopped working all of a sudden. And it still lights up and it powers on, but we're not getting any output, even when we put the device into bypass. So this is a pretty cool device to take a look at. We've got a pretty decent service manual for it that gives us schematics for most of the device, and we've got block diagrams for the entire thing. This is kind of a complicated device. It came out of Lexicon back in this one I think came out in the 90s. They did make digital reverberator starting all the way back in the 80s. Let's just take a quick look at the block diagram for this device. As we can see from this, we've got a few CPUs, we've got DSPs, and we've got some analog. We've got a V40, an NEC V40 host processor, that this is responsible for reading all the front panel switches and the front panel encoders and writing to the front display. Basically for your UI for the user to interact with, and that's handled by the V40. It doesn't really do much with the actual DSP program other than it is going to tell the Z80s which program to load into the memory for the DSPs. Other note here, we see we've got two Z80 processors, and it looks like each one of them is responsible for a Lexi chip. These are the actual DSPs, Lexi chip 2X and 2Y. Probably because this is a stereo effect, and we would have probably a DSP processing each channel. Fun thing to note here is there's some transfer registers between X and Y. I hope we really don't get troubleshooting this as far as the inner workings of the DSP board. We can if we have to. There are some parts on that board that we can probably still get. We could probably even get Z80s if we needed to. But there are some parts on that board we cannot get. So we really hope we don't have a problem with those, such as the Lexi chips themselves. Basically all these chips that say VLSI on them. These ones were custom contracted out by Lexicon back in the day, and we really have no chance of getting those. Even at the time this device was new, Lexicon did not make those available as service replacement parts. They had the whole DSP board, and that was it. So if anything went wrong on this board, you replaced the entire board. So that limits us a little bit into what repairs we can do. We can replace like Z80s and some of these other components on there we probably can get. Like some of them look like logic, some of them might be memory. So if we had to, we probably could. But we're hoping not to have to. And what we're seeing is we're not even getting a signal on bypass mode. So in bypass mode, it's going to go as far as the Lexi chip. Right, so we can see our signal's going to come in for our left and right. It's going to go through the level attenuator on the front panel. Then it's going to go through an analog to digital converter. And it's going to be a digital signal from this point forward. So here we're going to feed in a sine wave, and we should see a sine wave. After the output of the A to D, analog to digital converter, is going to be a digital signal. So we're going to expect a pulse train that comes out of there at a pretty regular, at a very regular frequency. And this apparently is going to have to feed in the Lexi chip. So there's probably some kind of functionality. The bypass button gets read by the V40, and we must be sending some kind of control signal to the Lexi chips to let them know that we're in bypass, so they can just send that pulse train right back out to a digital filter, then to a digital analog converter, back into analog, through an output stage, and out there. So hopefully, so it's still possible our problem is Lexi chips. We really hope that it isn't, because we can't get those. So Ideally, it'll be something simple with involving analog to digital analog converter, maybe op amp stage or something of that nature. So let's jump into the schematic first and see what we're going to deal with here, right? So in the schematic, let's zoom it up. So let's say we've got left input or right input. Looks like they're both feeding into IC U1, op amp U1. It's going to be a dual op amp, and looks like pin 1 and pin 7 are the two outputs for it. Okay, so let's take a look over on the workbench of the device. So what we have right here is U1, and these are typically labeled. You always can check the data sheet whenever you have a question, but the dot or the notch tells you that this is pin 1, and they're numbered counterclockwise going around from there. So 1, 2, 3, 4, 5, 6, 7, 8 on this particular one. Now, our schematic told us that we were looking for pin 7. So let's take a look at how we've set up the scope and the function generator. I've set up a 2 kilohertz test signal sine wave, and we've got it at about 130 millivolts peak to peak. This to give us a decent enough test signal to be able to find easily, but not so strong that we're going to be blowing everything out. So channel 1, the yellow channel, is on the input. It's connected to the input with the function generator. So the function generator, the scope, and the right channel input of the Lexicon are all connected together. Now, channel 2 on the scope, I removed the ground lead because I don't need it. I don't need that dangling around. I'm just using the probe, as you can see. Just a probe end without the clip on it, so that I can probe around. Now, you do need to be extra careful here that you don't short between pins. You don't short between pins using the end of the probe, right? If you touch between leads, you short those leads together. Depending on what those leads are, that could be a problem or it might not be a problem, but you need to be careful not to do that. Additionally, on this scope, channel 2 is the channel that we're going to be looking for our signal with. Right now, I've got channel 2. I'm going to go over and touch the input right now, just to input right where we have channel 1 connected as well, and the function generator. And as you can see, that's adjusted so I can see the test signal, right? So if the signal is there, I will see it. So when I go probing around for this signal, I shouldn't be adjusting the vertical scale and the horizontal scale on the scope. If the signal's there, I'm going to see it. If it's not there, it's very important that we don't go hunting for it. Now, the amplitude could change some. It can get somewhat smaller or somewhat bigger. And we'll kind of have to make sense of that on the schematic, too, to see what we expect to see, right? But it's pretty important that we don't go hunting for this signal, because as you can see, it's noisy as heck, right? And if we just go zooming like crazy, we can find all kinds of things that our brain will tell us must be the signal. But unless it looks like channel 1, unless it's already right, nice and strong and right there, it's not the signal. So our schematic told us that the right channel should be going through this op amp right here, U1, and coming out, the output of that op amp will be pin 7. So right here is pin 7, and as you can see, boom, we've got the signal on channel 2 of the oscilloscope. We didn't have to hunt for it. We can see it's right there. All right, we are good to go. And it does make sense that this looks to be about unity gain. It does kind of look like a buffer configuration for the. I mean, there is a negative feedback loop there, but there isn't an output resistor though. So it does kind of make sense that this would be about unity gain. So excellent. So we've seen that that is good. I'm just going to quickly switch while we're here. I'm just going to pull the lead out of the left channel, the right channel, and put it in the left channel. And the scope, the schematic told us that pin 1 is the output of that channel. So let's just go ahead and take a look at pin 1. And boom, we've got it. All right, so now we are test signals in the left channel. So let's take a look back at our schematic. So we have tested here and there, and we know the signal is good. So now we see that these two go through J4 connections 7 and 1, right? So LN, RN. So now we've just got to figure out where those go on the schematic, right? LN, RN. So it looks to me that the next place these are going is going to be, and we're in the left channel now, is going to be going to U5. If we find R29, we can just double check that we see something at R29. And we want to look for U5. And U5 is another op amp. Just try to get an idea of what that op amp looks like it's doing. So it looks like we're conditioning a signal before it gets into A to C converter. So let's take a look at LN, R29, and U5. And we can go back to the circuit board here. 18, U6, U5. All right, so here we got R5 of U5 right here. So what we're being told on the schematic is on pin 1 of U5 we should be seeing an output. And sure enough, we've got our test signal. And it looks good. It's so next interesting spot on this schematic is going to be U6. Pin 7 of U6 is going to be the output there. Let's see what that looks like. Or R25. If we see R25, we can check there. It's the same thing, right, as pin 7 of U6. So let's take a look at what we have for that. Switch it back over to circuit board. U6 is right there, right next to it. That's our U6, and we want to look at pin 7. And that's interesting, right? Now that we do expect to see that, we have an inverting op amp configuration. So we have the same signal, but it's inverted, or 180 degrees out of phase. So that looks like that's working too. And this makes sense. If we look back at the diagram here, U5, which is a non-inverted signal, is going to go and feed into analog input left positive on the ADC, and this inverted signal from U6 is going into the negative. So we're feeding a differential signal into the ADC, right? So the ADC is going to be able to sample this really nicely because we're really exaggerating the voltage differences between the high and low there. So and it looks like we're going to be doing the same thing to left and right, right? So U5 and U5, right? This one was U6 and U5. Looks like this is U5. U5. Yeah, this had to use another chip there. So we can take a look at these two while we're there, right? So I'll pull my test signal out of the left channel, and let's put it into the right channel. And we're going to look at pin U5, chip U5, pins 1 and 7, and we're going to expect to see a inverted signal on one and a non-inverted on the other. So let's go back to the circuit here, and it was again on U5, so pins 1 and 7, we expect to see the opposite. So 1 is non-inverted, and 7 is inverted. Probably if we want to make that stand out even more, that it's inverted, you can see that they are the opposite, right? This is an inverting op-amp configuration. And pin 1, you can see that it's non-inverted, right? They match up. So this is excellent. So we've got signal all the way up to there, right? And what we expect to see, if we go back to the schematic again, we expect to see this inverted and non-inverted signals go to pins 25 and 26 of the ADC. And this is going to be the end of what we expect to see for analog. So we can at least trace it that far and just see that we got no problem with the trace. So 25 and 26. Alright, so the ADC is, we'll switch back over to the other camera view. The ADC is a little bit buried behind these there we go. So this right here is our ADC. So we got to count pins. So pins 25 and 26, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. So here's 25, and there's 26. As you can see, there's our inverted and non-inverted signals. So those are getting to the ADC. So now our big question is, what do we expect to see coming out of the ADC? I said a minute ago, we can't really be hunting for a signal, right? But now the signal that we're looking for is got to be different. It's got to be different than the analog signal. So what are our scope settings that we should have to look for that signal? Well, for one, let's just try to figure out where our output of this ADC should be, what pins it should be, and then we'll go from there, right? Let's go on to the main screen. We'll go back to the schematic. And we've got a lot of pins, but we've got a few pins that are going to be our outputs. Our S data is the serial data. So this is pin 15 is where our data should be coming out. Also R32 is another place we can look, but pin 15 is where our data is coming out. So, I mean, first off the bat, let's take a look at pin 15 and see if we've got anything on it. But of note, pin 14 is the serial clock, right? And pin 13 is a left-right signal, right? Asserting whether or not the serial data is for the left channel or the right channel. It's going to flip-flop back and forth between the two channels. It's going to put out so many bytes of left, so many bits of left, and then so many bits of right, so many bits of left, so many bits of right. And then the clock is going to be for what each bit is, the time period for each bit. So let's just first take a look at pin 15. And we also know that pin 14 is the clock, and we know that pin 13 is the left and right. So we've got 3 pins we could look at to try to get an idea. And we'll try to hunt as little as possible, but we will have to adjust the scope to look at this data, because it's not going to be in the same time domain. It's probably not going to be as slow as the analog data is, right? It's not going to be a 2 kilohertz signal. It's going to be probably much faster. So let's take a look. Let's take a look at this chip and see what we got going on here. So again, pin 15 is going to be this pin right here on the end. So let's take a look at that pin and see what we got. Okay. Well, we expected something faster, so maybe that's fine, right? So let's expand out our time domain a little bit. This doesn't look very good, right? This doesn't look like I expected. And we're getting a crude measurement of somewhere in the 20 megahertz range, which doesn't sound quite right. So let's kind of go back. Let's go back and let's try something else, because maybe we found the problem, right? That did not look very good. We've got something. Let's take a look at the clock, right? The clock is going to tell us, if we've got a clock signal, it's going to tell us exactly where the bits are going to need to be. So that's probably going to be a good place to look. So pin 14 is the clock. So let's take a look at pin 14. And this looks kind of more promising. I'm going to do an auto set here and see if we get something. Now that looks a lot better, right? Let's hit measure here, wherever the measure button is. Yeah, 3 megahertz sounds more reasonable. Now we can kind of ignore channel 1 right now, because we are zoomed in to the point where we're just looking at the noise within a sine wave. So we honestly don't care about channel 1 right now, other than to know that we still have a signal. So I'm just going to turn channel 1 off, because it's actually distracting at the moment. We're not in that domain right now. So this is our clock, and this looks like a pretty solid clock. I mean, there's a little bit of ringing, but this is a 3 megahertz clock on a large-scale component board like this. I mean, I kind of expect there to be a little bit of ringing. So I kind of like that signal there. So what we can do from this is, so we see that it's like 7 volts peak to peak, and we got like 3 megahertz clock. So now, using this setting that the scope is at, this is what we should be looking for our digital data in. Because what we would expect to see now with this digital data would be that, and I'm gonna give us a different camera view here. Let's just take a look at the scope reading more directly here and see if I can hold it here. So our digital data, what I expect is that when it goes high, it should be at this rate. There's going to be a bit in each one of these spots. It's just that sometimes this might stay low. If the bit's a 0, it's going to stay low. If the bit in that spot is a 1, it's going to go high. So we could have like a few ones in a row, a couple 0, a couple more ones, right? But we expect it to be, we should see something with these scope settings though. We shouldn't have to change our vertical scale or our time scale in order to see the bits on the output stream. So I'm going to switch back over to pin 15, which is supposed to be our data that's coming out. And now I'm not going to adjust the scope anymore. I don't want to hunt for the signal now. I use the clock signal to see if we should see something or not. And you know what? And sure enough, we aren't seeing anything. We're not getting any signal there. Remember how before it kind of looked like we had a signal when we went hunting for it? And I said, well, these settings were zoomed way in, right? We were looking at noise on a dead pin is what we were looking at. And sure enough, if you zoom in enough, it kind of looks like something. But as we can see here, by using we were lucky. Our clock pin is good. We are getting a clock signal. So we use that to set the scope, so we know what our zoom on the scope needs to be, what our time scale needs to be, and what our voltage scale needs to be. And then we can go over and go back and look at that output pin, right? Let's take a look at another pin. Let's look at the left-right pin, right? Now I might actually want to zoom out the time scale just a little on this one because this is going to alternate between 0 and 1, or low volts and high volts, much more slowly, right? And I'm pretty sure this is an 18-bit ADC. So we should see 18 bits, right? We should see 18 of these transitions would be low. Then that LR pin switches, and then we have another 18 clocks. And then it switches again, and we have 18 clocks, right? So that's pin 13. So let's try pin 13. And so there we see one transition, right? Just like I said, it's going to be slower. So let's just move our time scale back out. And there we go. We are seeing our left and right pin go. What might be kind of neat to look at, and I'm going to pull my channel 1. I'm going to get channel 1 back on. And I'm going to put channel 1 on the clock pin. Let's take a look at channel 1 on the clock pin. Okay, so let's zoom in a little bit. I'm running out of hands to use, so let's see if we can get zoomed in a little better. And that's probably about 18 of them, right? Let's see if we can roughly count the 18. So we're just barely off the edge of the screen there. It might be more than 18. I might have the number of bit resolution of this thing wrong. But as we can see, we're getting a bunch of clocks with it high and then a bunch of clocks with it low, right? And that's what we expect to see. So the LR signal coming out of the ADC looks good. The clock signal coming into it looks good, but there is no output signal. And we've got good analog signal coming into the ADC. So this looks to me like the ADC isn't any good. But we can do one more thing to verify. I'm going to turn the power off on this board, on the PCM90. I'm going to pull out this ADC chip. I'm going to pull out this ADC chip and make sure the pins are okay. But I'm going to take this pin 15, which is our output. I'm going to bend it out. Because one thing I'm curious about is whether or not something on this board is maybe holding this pin low, and this ADC is not able to pull the pin up, or is it just not getting any output out of this? So I've just pulled that pin so that it sticks out, right? And then we'll put this back in the socket and carefully put this back in. We'll make sure that pin isn't touching something that it's not supposed to touch either. Alright, it's not touching anything, and it's out of the socket. So now we'll power this thing back up, and we're going to see if it gets through its there's a little diagnostics when it powers up. Alright, we finished the diagnostics, and we're going to go into bypass. Okay, so we've still got our clock signal, we've still got our LR signal, and we still don't have an output signal. So pretty confident to say that it's actually the ADC that's bad, so I'm going to power this back off again. And pull this ADC chip out. I just so happen to have another ADC for this thing, because I already checked this thing out and knew that the ADC was bad, so we had to order this from overseas because they don't make this anymore. So hopefully this one is good. We had got it from Hong Kong or from China, I forget which. Alright, CS5389 KP. CS5389 KP. Alrighty, so we'll let the thing power up. Go through its self-tests. And we will once again alright, we're on. Oh, and look at that. So here we've got our clock signal. And I'm going to again turn off channel 1 for now. So that's our clock signal, and what we expect is in each one of those spots the signal could either be high or low, and it'll alternate. Sometimes it will be high, sometimes it will be low. So here's our output pin, and that's what we expected to see. That's what we expected to see on that pin. So this ADC is providing output. That's excellent. So something else I wanted to talk about here is when I saw the scope output after we fixed the ADC, and I said that looks good. It's what we want to see. How is that what we want to see? Unfortunately, I didn't zoom up at the time, so I had to kind of expand out the corner shot of the scope right here. So it's a little pixelated, but I think we can still make out what we need to see here. So what we saw was a scope output that looks like a lot of rectangles, right? It's like we got a line up high and a line down low. We got some random vertical lines in it. And now, if we remember correctly, the
the clock signal, when we looked at the clock signal, we were seeing something that looked like this, basically. You know, roughly like that, right? And actually, at this scope, it actually may have been double that, but let's just go with this for now. And this kind of goes along with that, right? Like we've got bits where we expect to see them. But why aren't we seeing something that looks more like this? I said we want to see a pulse train. Well, that is what we're seeing here. But the thing is, the way these scopes trace, let's say we're just the lines that they draw are persistent for a certain period of time. So what we're seeing in here is a bunch of scans across the scope. So when it scans across once, let's say it comes in like this, and this is a 1, and then we go down to maybe a bit that's a 0. Maybe we go a couple bits in a row that are zeros, and then we have maybe a couple of 1s in a row, and then we had a 0, and then a 1, and we finished out with another 1. So then when it scans across, it's up here, and maybe we had 2 1s, and then we go to a 0, and maybe we had 3 zeros in a row, and then we go back up and we have a 1 bit, maybe another 1 bit, maybe go back down for another 0, and then that comes in over here, and maybe there's a few zeros in a row, and it goes up, and there's a 1. So you get the idea here. There's each one of these bit positions could be a 0 or a 1 at any point in time that it scans across. So that's why when I saw this pattern on the scope, I said that this is what we expect to see, because this is a data stream, right? The clock signal we expect to be regular. It's going to be, every time it scans across, it's going to be 1 0 1 0 1 0 1 0 1 0. That's a clock. But the data stream, the serial data, we don't, it's not arbitrary. It's based on the signal, but it's not going to be the same sequence every time the scope scans across. So we're going to kind of see, like this kind of pattern, we're going to see some of these vertical lines flicker on and off. And but what we did see is we saw solidly going up to a logic high voltage and a logic low voltage. And we saw, lines that kind of went away and came back in between, right? So this is what we wanted to see. I didn't have a good way to connect up the reverb unit to the computer right now for the recording, but I did test it out, and the reverb unit does work, and it sounds really good. So this did successfully fix the problem with the reverb unit, so we can call this repair a success. I just wanted to touch a little bit more on what the serial data is supposed to look like on the scope. So thank you for watching, and we look forward to doing some more repairs on the bench here soon.